In our continued study of integrated circuit chips, we're looking at logic gate flip-flops. In our previous lessons of logic gates, we saw that we can combine logic gates to make decisions depending on their inputs and their logical outputs depending on the nature of the relationship of the expected inputs. To review, here if A or B is true, then Y1 is false. And if C or D is true, then Y2 is false. But what would happen if the output of Y2 was connected to one of the inputs of Y1? It appears our original truth table can be tossed away, for clearly this is not behaving like before. This is to be expected because we have changed the input and logic flow. But carefully observe the output Y1. Let's make one more change. Let's tie the output of Y1 to the input of Y2, like we did before. Now the two switches are working together to make the outputs flip states. This is one of the fundamental arrangements of logic gates. It has the possibility of storing and moving data, albeit one bit at a time. For our last trick, we're going to replace the manual switches with a pulsing clock and a NOT gate so that each input will always receive the opposite value, just like turning one switch on and the other one off manually. Net result of all this work is we have created a unit called a flip-flop. It's a flip-flop integrated circuit. We're going to take a look at it and some of its younger cousins. A flip-flop is a latching and unlatching unit that changes state when triggered. It has two outputs, Q and Q0. It also has two input signal sources and requires a 5-volt DC supply to work. When the bottom signal pin goes high and the top signal pin is low, the IC chip changes the state of both Q0 and Q. The Q0 pin is set low and the Q pin is set high. On the next signal, the top signal pin is set high and the bottom signal is low. The IC chip then sets Q low and resets Q0 high again. From the basic flip-flop, a series of flip-flop ICs can be developed whereby the storing and resetting of data allows the flip-flop to store data and release it when required. Introducing the RS or SR flip-flop. The RS stands for reset set. There are two different construction methods available where either NOR gates are used or NAND gates are used. Notice on the NAND version, the NOT bars are used on the set and reset pins as well as the Q0. The two different gates work in the same fashion. The outputs are intended to be complementary. That is, they are opposite each other at any time during the process. Both the NOR RS and NAND RS must have opposite states appear at the set and reset pins to work effectively. Let's follow these truth tables to see how the RS NOR gate works. We see we have the reset, the set, our Q, and our Q naught. In the actual box, there is no line above the Q, but it is red to indicate it is the Q naught. When the reset and set inputs are both 0, the flip-flop will maintain the last state of the Q and Q naught outputs. When R goes high, it does not affect its output here. It does not change its output. When the set goes high, its output goes low. This results in reset's output going high. Should the reset go high as well as S, an ambiguous state is created, as both outputs will be 0. Therefore, the reset and set inputs can work independently, but this can introduce timing issues. This animation shows the result of uncoordinated inputs. At one point, the set and reset are low, which means neither Q or Q naught will change states. When both go high, the ambiguous state happens, which turns off both, resulting in data loss and inconsistency. This time, each is assigned a starting condition, and each input is always opposite each other. This results in a much smoother and predictable operation. The RS flip-flop is vastly improved with the addition of a clock input pin. A clock signal is like heartbeat in that a steady pattern of equally spaced and timed high-low pulses are generated and used to synchronize all the devices that are using that signal. If we start with a simple RS flip-flop, we know that Q and Q naught should always be complementary. But how do we make sure that they're always triggered together? Well, we add AND gates. If you take two AND gates and tie one of their inputs together, you create a common clock input point, identified here as E. Since each will receive a 1 or a 0 at the same time, they will always be ready to trigger the reset and set pins. Other AND gate input pins are used to receive the reset and set pin data and pass it through. Since the only time that either gate will operate is when the common tie E and the input to the set or reset is high, you have created a predictable and steady flip-flop. This flip-flop is also known as the gated set-reset flip-flop. You can see by looking at the truth table how this data gets moved. When E, our clock signal, is 0, then neither the set or reset changes its data, and then Q and Q naught do not change. When E is set, if S is 0 or 1, or if R is 1 or 0, that data is moved to our Q or our Q naught. So someone figured this out and created a new flip-flop. If a NOT gate is placed in series with the AND gate of the reset, but in parallel with the set, the flip-flop will not pass data on the next clock pulse. The data must cycle through a normal reset first and then pass the data. Hence, the name delayed flip-flop, or D flip-flop for short. All right, so let's go through this step by step. So first of all, when the data bit is set, the bit is not passed until the clock bit is also set. We have to keep that clear in our minds. Okay, so step 1, there is data waiting at the data pin, the D pin. Step 2, when the clock goes high, the data is moved and stored in an internal latch. Step 3, you have to wait for the second clock cycle, and then the data is moved from that internal latch to the output. As mentioned earlier, with simple set-reset flip-flops, there is always the possibility of having an ambiguous state. To be truthful, there are actually two ambiguous states. When both R and S are high, well, that's not allowed, or when both R and S are low, there's no change. To fix this, we're going to turn to a little friend we have called the AND gate, but we will use a 3-input AND gate. That and the addition of a clock pulse circuitry and the feedback of each output to the other's input prevents the illegal or invalid output conditions. While the feedback effectively nulls out the ambiguous state, we're not quite there yet. We have data waiting at the J and K pins. We need a way to trigger the flipping and flopping action to move that data like the reset and set pins of yore. Well, fortunately for us, thanks to the inventor Jack Kilby, he solved the problem by adding two pins called preset and clear. So what Mr. Kilby ended up with was the JK flip-flop. The JK flip-flop combines the functionality of both the reset and set and delay flip-flops, and it also has a clock input that feeds a steady signal that prevents any ambiguous signal state, and the preset and clear provides the functionality of the set reset. When in operation, data set at the J input is ignored until the clock pin is on, that is, the rising edge. At the same time, the K input must be 0. When this happens, the data is pushed and the output Q becomes true. If K is 1 and J is 0, then at the next clock pulse, J is cleared and a 1 is placed in the not Q output. The JK uses leading edge detection. This means the status or change of state occurs the instant the clock pulse goes high. With our JK flip-flop, we now have a successful way of storing and moving a single bit. Now that we have that method, we can form a series of internal storage bits and move them in and out. If a string of JK flip-flops are put together, we can make a very simple shift register. The tied clock signals can trigger every JK flip-flop to transfer their data to the next JK flip-flop, and you've just created a register. In the next video, we will be examining other uses of integrated circuits. Thanks for watching, and yes, it's on the test.